Hello and welcome back to Introduction to Physics Labs. My name is Paul Eric, and today we're going to be doing Lab 1.8a, which is entitled Energy and Motion. And if you've noticed, I've written up here some of the formulas that you should now be familiar with. So we did a lab in which you were able to predict the motion of an object if you knew its acceleration. And then these were the three equations of motion. So you had the how fast equation, the how far equation, and then the hybrid equation. Then we also did another lab in which you were able to predict the motion of an object if you knew its momentum. And linear momentum was given by the letter P, and it's equal to the mass of the object times its velocity. And then we had this thing that we called conservation of momentum, in which we said that the momentum that you begin with, initial momentum, had to equal the final momentum. Well, in this lab, we're going to learn a third way of predicting the motion of an object, and that's going to be by using energy. So the purpose of this lab is, one, to use conservation of energy to determine how fast an object will be traveling when it reaches the bottom of a ramp. Number two, to use the concept of work to determine how far a car is going to slide. And then learning objective three, to calculate the speed of a ballistic pendulum using conservation of momentum. And then four, to calculate how far a ballistic pendulum will rise using conservation of energy. So we're actually going to be using several of these concepts that you already should know about in order to do today's lab. So in part one of the lab, what we want to do is to, okay, you're going to open this link, or you could just go to www.physicsclassroom.com, but you're going to have to do a lot of searching in order to get to this. So it's probably better just to click on the link here. And then you need to click Begin Activity at the bottom of the page in order to get the program running. And then once you've done that, then you're going to have this. So this is what you should see. Okay, then you're going to click on 10 centimeters. So going back to here, we're going to click on the 10 centimeters. Okay, and there is the actual lab. And so what you got is, here's a ramp, here's a car. You're going to release it from a height of 10 centimeters. So you see it's got this grid here, and each of the squares is going to be 10 centimeters, either going up and down or going sideways. So when you click on this button, release button, it's going to release the car, and then it's going to travel to the bottom of the ramp. And then once it gets to the bottom of the ramp, it's going to go sideways. It's going to go inside this box, and then this box is going to slide a certain distance sideways. Now that's part two of the lab. So for right now, we don't care about what the box is doing. So we're only interested in the car, and then what is it going to be doing. Okay, so that this is what you should see, and then you're going to now go down to here. Okay, and so it says that 10 centimeters is going to be the height a car will be released from, and it says to record this height in meters, so you have to change it from centimeters to meters in the table below. Now the table below is really below, so you need to go all the way down to here, and so there is the table that you're going to be filling in. Okay, now the energy, so this is a new concept. So we've talked about what do we mean by distance, speed, momentum, and now we've got another concept called energy. And no matter what kind of energy we're talking about, it's always going to be the letter E. And then the official metric unit for energy is going to be called the joule. And so the energy it has at that height is going to be called its potential energy. And now, in order to put that down, we're going to say E sub P. And then in some textbooks, they might say PE. In other textbooks, they might use the letter U for potential energy. But the main thing is that it's energy of position. It depends somehow on the position of the object. So there are other kinds of potential energy, which we're not going to talk about. Well, I guess we're talking about it. But another one would be like a bow and arrow. So if you take the bow and you pull it back, you're putting energy into the bow. And so you notice there's a distance that you're pulling it. So similarly here, there is a distance involved, and that is going to be the distance that this thing is raised above the ground. And so our distance is going to be 10 centimeters, but remember, it always has to be in official metric units. So it's got to be in meters. So here's our formula, that the potential energy of an object is going to be M and then G and then H. Now in some textbooks, this is going to be maybe the letter Y for up and down, or it could be the letter R. I kind of like to use the letter R because that always means, I always use that for distance, but I'm using the letter H this time for height. And then G, you've seen that before, so that's the acceleration due to gravity, 9.81 meters per second squared to 3 significant figures, but we're only doing it to 2 in here. And then M is going to be the mass of the object. And then objects also are going to have a second kind of energy called kinetic energy. So this one here, so I'm kind of running out of room, so if you don't mind, let me just erase this, and we'll put it underneath it. And so this is a type of energy, so we're going to use the letter E, and then it's K for kinetic energy, and this is going to be energy of motion. So if something is moving, it has kinetic energy. And so this is going to be given by 1/2, and then M, same M here, and then V squared, where V is going to be the velocity. So right down here, what properties of the car does this formula depend on? And I guess I gave it away. So you're going to put that right here. So what do these two letters stand for? And then just put that in there. Okay, then we're going to say, so let's go on down a little bit further, that the sum of an object's potential energy and its kinetic energy is going to be called its total mechanical energy, which we're just going to say is the letter E. So E then is going to be equal to the kinetic energy plus the potential energy of an object. And the change in mechanical energy, so the change in E, so where can I put this at? So let's put it up here. So the change in its energy is going to be related to force. And it's going to be related in that when a force, now it's going to be an outside force, acts on a system and then causes that system to move a distance r, that's going to change the energy of that system. Now that should look kind of familiar, because do you remember when we did momentum, we said that the change in momentum P was equal to a force multiplied by time. And then these two things put together, that was called the impulse that was given to the system. Well, these two things, they go together, and that's going to be called the work of the system. So work W is going to be equal to these two things put together, and work changes the energy of the system like an impulse changes the momentum of a system. Now, if you don't get this, that's okay. All right, so we're not yet ready to, so this is just bonus stuff. Are you excited by this? I hope so. So I'm really excited. You can't really tell, but I'm really excited because this is mathematics, and it's just so good in physics. Okay, now, just like in the previous lab when we did momentum, we're going to say if there is no outside force acting on the system, then F is going to be equal to 0. And then that means that 0 times anything is going to be 0. So this side over here is 0. But then this thing here, change, means final minus initial. So we're going to say that the final energy minus its initial energy has to equal 0. And then we could take one of those energies over to the other side. And so now what we're ending up with is that your initial energy, now remember that this energy, E, is the potential plus the kinetic. Okay, that's what this is. Has to equal your final energy, and then this energy is both the potential energy and the kinetic. So this one is going to be called conservation of energy. This one was conservation of momentum, which resulted if F was equal to 0. And then this one is conservation of energy if F is equal to 0. So this means that the total energy that you begin with has to equal the total energy that you end with. And, well, I keep giving stuff away to you. All right, so what was, I just get so excited about this. So what was conservation of momentum, and under what conditions does it happen? So back me up if you didn't remember what I just said. So you can put that right there. All right, so now we're actually ready to do something. So what we're going to do is we're going to click on release. So we're going to go back to the simulation here. Click on release, and there it goes. Okay, and then do you see it went into the box, and it caused the box to move from position A to position B. Now you need to measure that distance. Measure the distance. Now remember the distance from one box to here, so that's 1 centimeter. So what's the distance from A to B? And so that's going to be the distance that the box slid. Now you're going to need that piece of information, so you want to write that down. You're also going to write down the speed of the object, and so you're going to put that right, or take that number from there. So that was the speed when it got to the bottom of the ramp, and you're going to want to write down that number, because if we go back to the lab here, and we got this down here, so we got the release height, so that's going to be 10 centimeters in meters, so put that there. You're going to write down what was the final velocity, okay, so you're going to put that there, but we're going to also calculate the final velocity, and we're going to put that right here. So I haven't showed you yet how to do that. And then we also have the distance that the box slid, and you're going to need to put that right there. So we're going to fill in this data table. Okay, so now let's go back up to here, All right, now this time I will try not to answer questions. Okay, so we've done this one, so we've done number 2. Okay, now we are ready for 3. What type of energy did the car have to begin with? So you got a 50-50 shot. So it's either potential energy or kinetic energy. So which type of energy did it start with? Okay, then number 4, what is the value, so what is the number for the initial kinetic energy of the car? So when it's at the top of the ramp, how much kinetic energy does it have? It's a very simple number. And why? Okay, because remember, the car is not moving before you click the release button. So that should be a hint on that. So what was the value of the kinetic energy that the car began with? And then when the car reaches the bottom of the ramp, what is the value of its potential energy? And it's a very simple number, again, because when it gets to the bottom of the ramp, how high off the ramp is it? Okay, and then if you take that number and you plug it into this thing here, so if the H is equal to, help me out here, if the H is equal to 0, because it's at the bottom of the ramp, then 0 times anything is, okay, so put that there. And then under these conditions, so let's go back to this equation, so that this is still going to be there because it was released from a certain height, but this is not. Okay, so that's going to be a 0. And then this one's going to be a 0, but you still have this one over here. Okay, so that what we're ending up with, our conservation of energy equation, is going to be turning out to be that mgh has to equal 1/2 mv final and then squared. So that is what we've got down here. So now we got that. Okay, question number 6. This equation can be simplified even more by doing something to the mass. You know algebra. What can you do? So you notice there's an m over here and there's an m over here. So what can you do to those two m's? Begins with a C, ends with Ansel. Put it together, okay? So now you've got this equation is going to be simplified even more because we can get rid of these two m's. And this is a very good thing. It tells us a couple of things. One, we could not do the simulation because did you notice that they did not give you the mass of the car? But we don't need to know the mass of the car because it canceled out. Another interesting thing is what would happen if you had a big, heavy car on the ramp and then you got a little dinky Volkswagen car on the ramp at the same height. Which one do you think would get to the bottom of the ramp first? It might surprise you. Okay, look at this thing here. You notice it doesn't depend on the what of the car. Okay, it's not in the equation. So that means we don't need to worry about it. So question number 8 is, let's see. Now I need for you to calculate the velocity of the car. So we're going to use this to calculate the velocity of the car. So what we could do is multiply both sides of the equation by 2. So then now we're going to have 2gh is equal to v squared, v final squared. And then what do we need to do? If this is squared, What's the opposite of a square? Okay, I don't want to give everything to you here. Square root. All right, so you're going to take the square root of this, and now you got that. So you've got the height in meters. You know what g is, the acceleration due to gravity, 9.81. You know what a 2 is, so multiply that together, take the square root, and you're going to get the final velocity it would have if it was energy was conserved. So if all of the energy of the potential was turned into kinetic, then that would be the velocity you'd end up with. But look at the velocity that you end up with this, doing this thing, the calculated velocity, and compare it to the measured velocity, and you'll notice that you got two different numbers. So I want you to speculate as to why the speed is slower than what it should be. Okay, it's almost as if there was some energy that we're not accounting for. And so what do you think that energy is that is slowing it down as it's going down the ramp? And so go ahead and put that right here. Now, does this mean that conservation of energy is being violated? So now what we need to do is go back up to this statement up here. Conservation of energy says that if there is no force, then the energy you begin with equals the energy you end with. But that's not happening here. So that means there must be a what? And what force do you think that is rubbing up against the car as it's going down the ramp? All right, now you're going to repeat part 1 for 20 centimeters and then repeat it for 40 centimeters, so that you're going to fill in all of this information here for those two things. All right, and it's important that you do this because there's going to be some questions at the end of the lab you'll be able to answer if you know that information. So that was part 1, and now we're going to take a break, and when we come back we will do part 2 of the lab.